Now let us understand, with these kind of emitters, what are the parameters that are important that I need to know from the field emission guns or from the thermionic gun, from the thermionic electron gun. So there are three main parameters that a source or an electron gun controls in an electron microscope. Now, whether it is a scanning electron microscope or a transmission electron microscope, these three parameters do matter a lot for the kind of imaging that you want to do or the kind of analysis that you want to do from a microscope. The parameters that are mentioned here are, brightness, stability, and coherency. Let us understand each one of these one by one. So if I talk about coherency, there is something called as temporal coherence and spatial coherence. Now what exactly is temporal coherence? If I have a source and when I am extracting electrons from this, so if the electrons that are emanated are all sort of in phase, that is, let us say I apply a potential of 3.5 or 4 kilovolt, I get electrons being emitted, and then there is some wavelength, and eventually I accelerate it over a potential of 200 or 300 kV. Accordingly, the wavelength of the electrons that are emanating from the source are going to change. Now, if I have an extremely stable high tension system, I can sort of maintain this coherency reasonably well, but also when I have the double anode system like in a field emission gun, I can sort of have a better feedback control and maintain the coherency much better in a field emitter. So you need a stable voltage, and there is something else called as a monochromator which you can add to improve the temporal coherence. Essentially, when I talk about temporal coherency, it simply means if I have electrons that are emanating over a solid angle, if I can maintain the wavelengths of all the electrons that are emanating more or less within the same range, I can say that the temporal coherency is good. The second parameter is the spatial coherence. How can I define the spatial coherency? If I call it as DC as the spatial coherency, let us say I have electrons of a wavelength lambda, they are spread over a solid angle alpha. So the same electrons which are emanating over the three dimensions beyond the electron gun, let us say are now emerging over an angle alpha. The smaller the region from which I have the emission of the electrons, that is, if I draw a comparison within a lanthanum hexaboride filament which was lying like this versus a sharp tungsten needle, the electrons that are emanating from the sort of 110 plane of the lanthanum hexaboride crystal versus the 310 of a tungsten filament. Typically you have something like a trimer which is formed at the tip of a tungsten filament, and you have emission happening from a very small point. So this is called as the spatial coherence. Now if I take a step back and recollect the construction of a field emission gun, when the point source is extremely fine, I would have a much more spatially coherent image that is formed beyond the field emitter. So within a field emission gun, my spatial and also the temporal coherence is significantly better than I have from a lanthanum hexaboride filament in a thermionic emitter. One could argue that because there is one particular crystallographic facet over which I have emission happening from a lanthanum hexaboride filament, probably my temporal coherence is actually not too bad in a thermionic emitter, but the spatial coherence, because it happens from a much larger area, is much poorer in comparison with a field emitter. So this coherency in fact again plays an effect on the resolution within a microscope. Before I introduce brightness, let's have a look at the other parameter on the current stability of a source. If you have an unstable source, what happens is, while you're imaging, you've seen in the previous videos from a thermionic emitter, after there was sustained emission, you had constant illumination on the fluorescent screen there, and your emission currents remain stable. But if this is fluctuating, if the source is not stable, what you would have is, you would have some kind of funny effects while you're recording the image. You would not have stability and constant exposure while you're recording the images as well, and it makes it sort of counterproductive when you're trying to record images from a sample. You might spend a lot of time on preparing a very good specimen, but if your source is not stable, especially if you're doing imaging on a sensitive material like a biological sample, you might have issues where your sample might be damaged, or the area of your interest might be lost, or there could be various effects. So if I look at thermionic sources, they are extremely stable with more or less 1% fluctuation in the emission current over a period of 1 hour. When I look at Schottky figs, the thermal figs or the Schottky figs, I would have a stability of more or less 1% over a period of an hour, but you would also have drift of these field emission guns. If I compare the same with cold field emitter, because you need much more stability of the vacuum in a field emitter, the stability is somewhere around 5% over an hour. You can maintain still the stability within field emission guns by having a zirconium oxide coating on tungsten tips. But even if I draw a comparison within thermionic emitters versus cold field emitter, I gave you an example that the emission current of a thermionic emitter or a Schottky fig, it remains stable once I have a sustained emission. But in a cold field emitter, once it is on, over a period of 2 or 3 hours of operation, your emission currents would drop. So if I'm trying to do an experiment where I'm kind of recording an in situ movie over a large period of time, please bear in mind that I would prefer stopping the experiment after 2 to 3 hours. I should do a flashing of the filament again in a cold field emitter and go back to the emission currents with the values that I get at the very start when I have a flashing. As an example, on one of our cold field emitter TEMs, I can tell you that you would have something of the order of 15 microampere emission current when I do a flashing, and over a period of about 2.5 hours, this would drop down to as low as 8 or 9 microampere per square centimeter. That is the measure that we have in our system here. And if I'm doing some kind of analytical study where I want very high emission currents to get a very good analytical signal, it becomes imperative that I know the range of time over which the emission currents are stable. Now, when I talk about these emission currents, that naturally steps into the next parameter which I'll discuss, which is the brightness. When I talk about the brightness, bear in mind in the example or the video that I showed you, the bright screen that is filling up my screen, I can spread it over an area, and spreading this over an area on a fluorescent screen is not actually controlling the brightness. Brightness is actually controlling the amount of electrons or the flux of electrons that are emanating from the source over a solid angle. Now this is sort of defined for every microscope. Just at the exit point from the field emission gun, you can measure the brightness by inserting a sort of a Faraday cup and check how much emission you have over a solid angle. And as it goes down and as it hits the fluorescent screen while it is going through the illumination system, you can spread this electron beam or you can converge the electron beam over a point. So the brightness can be the measure of the electrons more or less at the first crossover point beyond the field emission gun. Once it goes through the condenser and the illumination system of the microscope, I can naturally converge the beam to a point or spread it by turning the intensity or the brightness knob. Although it is written as the brightness knob on the microscope console, you are not actually changing the brightness, but you are changing the intensity of the electrons that are spread over an area. By changing the spot size, what I am doing is I am changing the size of the crossover point at the condenser lens, or the first crossover that is formed beyond the emitter. That is where I am controlling the brightness. There are a few parameters like gun lens, gun tilt, which are changed within the electron microscopes, and this controls your brightness. There are various ways in which you can control the brightness. So if I talk about brightness or the intensity, like I was just mentioning to you, strictly speaking, brightness is the flux or the current density from the source over a unit solid angle, and intensity is how bright and how large area you are spreading the beam on. This brightness is a critical parameter for any kind of analytical studies you do, and it is also important for getting much better or finer resolutions in STEM imaging. Now, if I talk about having a better brightness, the more brightness you have, you might actually have a much stronger analytical signal, like the inelastic electrons or the characteristic X-ray that is emanating from the sample, which is used in quantifying what kind of elements are present within a sample. Whether it is imaging within SEM or imaging within TEM, the beam currents or the probe currents play an important role on the X-rays that are emanating from a sample. Always when you are planning to do this kind of an analysis of your sample within an electron microscope, please be sure that you check the beam current, the energy spread, the area on which the interaction is, the interaction volume is, because when you get a map from a particular area from a sample, depending on how bright your beam is and how your crossover point is, or how spatially coherent your beam is, it decides on the overlapping area between two successive points when you are mapping to get the analytical information from a sample. So it is a trade-off between how much spatial coherence you want and how much brightness you want and how much beam current can your sample withstand versus how much signal is coming out. A combination of all these parameters together actually helps you get a good analytical signal. Now, if I define this brightness as the current at the source, this is spread over a solid angle. Let us say the crossover point, if I define as having some kind of a diameter, it is spread over an area, and you can define the brightness of an electron source as some emission current, IE, over pi d square by 4, which is the area on which you are measuring or the solid angle that you are measuring. This is typically measured in some ampere over square meter steradian. This would be your unit of brightness, whereas when I talk about intensity, I can simply measure it as some ampere over centimeter square. So that is about the parameters and the analytical imaging modes that are affected depending on the quality of the source you are using. If I draw a comparison between the thermionic source and the cold field emission sources, please remember the following parameters: the DC and the brightness and the D naught here. Let us see how you can roughly define them when I draw a comparison between a thermionic emitter and a field emitter. So if you look at this, here is an image from a fluorescent screen of a thermionic source. I have gotten this image by inserting a condenser aperture of 200 micrometer. So this is typically called as the C2 aperture in an electron microscope. And if I do the same, this is the same with a 200 micrometer C2 aperture in a field emission microscope as well. You can see that at the edge of the aperture, I do not have a very sharp boundary. In fact, if I draw the intensity profile across this, it is appearing like it is spread over a larger area, but I can see that it is much narrower and much sharper, and you can see some kind of an edge or a shadow here. Now, when I'm aligning my condenser apertures, you would see shortly at a later stage when I'll show you the operation and basic alignments of a microscope, these kind of parameters help you in aligning your condenser aperture and also your condenser astigmatism much better within a field emission source than your thermionic emitter. Let us have a look at the crossover point that I was talking to you. I am not looking at exactly the specific location at the point before my objective lenses or just at my condenser lenses where the first crossover is, but I am now transmitting the image of the first crossover point through the illumination system of the microscope, and I am projecting the information on the fluorescent screen and seeing how the intensity changes as I am changing the intensity knob or I am converging the beam. So let us see in the first video here, when I converge this, at this particular point, I have the crossover which is appearing the brightest here. Bear in mind, for this particular operation, I am not changing my brightness, but I am changing my intensity. So the current over some area, so ampere per centimeter square is changing here when I spread my intensity knob, and I can call this as the crossover point. So let us say if it is over this particular value and I call this as some D naught, I would have a similar effect in the field emitter, where my crossover point is going to a much smaller point. My D naught here is much narrower in a field emitter versus a thermionic emitter. I was actually using the same field of view and the same magnification and the same kind of a condenser aperture, but the brightnesses, the value of beta, which is over IE, which is ampere over meter square steradian, in both the cases, if I say beta thermionic emitter versus beta field emitter, this beta value is much higher here than in comparison with this. But this image I know is from a cold field emitter, and this intensity that you see drops over time, and my emission currents or my both brightness and my intensity drop over time here. So as you can see, if I just run through the videos again, this particular point here and this particular point here give you an impression of how much better probe you can have, or how much sharper probe you can have for getting better resolution or better analytical signal within a transmission electron microscope is. So I think with this point I'd like to end this discussion on the sources. To summarize, you have two broad kinds of sources. You have the thermionic emitters and you have the cold field emitter. The source actually plays an important role on the coherency. The coherency again has two kinds, which is temporal and spatial coherency, and the brightness of the source, which will play a role on the analytical signal I get, or the number of counts per second I get when I'm collecting characteristic X-rays in SEM or a TEM would change. And the third parameter which we talked about is the stability of the source. The thermionic emitter, when I talk about stability, this is not the lifetime of the source overall. There are ways in which the lifetime is prolonged. In fact, one could argue, I've just mentioned that the cold field emitter would run over a period of 7 years or so. The point is not how long the source or the field emitter gun is running. It is about how stable the emission current is remaining over a period of time. In a cold field emitter, I was mentioning that the brightness or the current drops over a period of 3 hours or so, whereas a Schottky FEG or a thermionic emitter, once I have a sustained emission, it would remain more or less with that particular emission current over a prolonged duration. Typically, a thermionic emitter runs for a period of around 1500 hours or so, and you simply change the filament. You would still have emission from a tungsten filament after the lanthanum hexaborate filament is exhausted, but you will lose out on the coherency significantly, especially the spatial coherency there. You would still have some kind of an emission, but your instrument resolution dies down if you do not replace the filament after you go past the lifetime of about 1500 hours. But the emission currents in a thermionic emitter would remain stable after I have the sustained emission. Then you have the Schottky emitter, which once you switch on, you keep it on, and you would have a stable emission, and a Schottky emitter coupled with a monochromator would give you an excellent combination of very good spatial coherence, very good temporal coherence, and a reasonable lifetime. But this is kind of a more expensive package. And then you have a cold field emitter where you're flashing the filament every day during the operation, and the entire gun assembly, you could prolong its lifetime for over a period of 7 years, but the operational current densities that you have to do periodic flashing and plan your experiments accordingly. So to summarize, that is all you have about sources. In the next lectures, you will see about electron lenses and a little bit about the image formation physics. Thank you.